Good morning to everyone. Today we are going to see graph autoencoders and graph variational autoencoders. And first I'm going to introduce you the idea of autoencoders. Then we will move to graph autoencoders, also known as GAE, the theory. Then we will go to some practice. Later I will show you variational autoencoders, the general idea. And then we will move to variational graph autoencoders and some practice and simple example using PyTorch geometric. Also, I want to show you Tensorboard. That is a tool really useful in order to compare models, and you can do a lot of stuff, but we will see later. Let's start. Okay, what does a deep neural network do? Well, the real thing that a deep neural network is that it learns important feature from the input. What does important feature means? Features that allow to do a specific task on the data, like classification or regression, whatever you want. But the idea is that a neural network learn important feature to do some task. So the question is, can we compress our input data? Like, for instance, suppose you have a bunch of document and you want to compress this document in a low dimensional vector, or you have images and you want to compress these images in a vector, in a low dimensional vector. Yes, we can do it with an autoencoder. The first thing I want to say is that autoencoders are neural networks that work in an unsupervised manner. What does it mean? It means that we don't need labeled data. So, for instance, if we have these images of cat and dogs, we don't need to know a priori which are cat and which are dogs. And it's quite useful because it's easier to have unsupervised data instead of supervised data, labeled data. That is, how can they work without any labeled data? Well, the idea is that our input, in this case, is an image, goes inside the autoencoder, and the autoencoder tries to reconstruct our input. So, as you can see, the input here is a dog, and the output is still a dog, is just ruined, let me say. But this one is the idea. Okay, how this autoencoder is done? Well, it's a neural network, as we said. We have an encoder that takes in input our data, our image, document, whatever we want. The information is encoded in a small dimension. Then we have a decoder at the end. And in the middle, we have our embedding. That is a representation of our data in a latent space of small dimension. Okay. And how it works, I just said, we have an input. The input goes in the encoder. The encoder produces an embedding, like in this case 1 and 5, for instance, and then the decoder tries to reconstruct the input. Okay, so how can we train this model? Well, we want to have this some kind of similarity between the input image and the output image, and we want to maximize, in this case, the similarity between the input and the output. In other words, we could want to minimize the reconstruction error. Okay. Okay, how can we use an autoencoder? Well, we can use it just to encode an image, and then we can use the representation to do whatever we want instead of in the domain of images, document, but we can do in a real domain of small dimension, like we can do clustering, visualization, whatever we want, but in another domain. Okay. Let's see how they works. First, okay, we have done. And we can now move to graph autoencoders. Okay, I think we have understood the idea of take the input and compress it and then decode it to obtain this embedding in a latent space. Let's talk about the graph. Suppose we have the structure is the same. We have an encoder, an embedding, and a decoder. Okay. Let's see, as you know from the previous lecture, we cannot use a simple convolution on graphs, but we have to use graph neural network. In fact, our encoder is one convolutional graph neural networks that produce a low-dimensional embedding representation of the input graph. Let's see how it's defined. This we have a graph convolutional network that takes in input A, the adjacencies matrices of the graph, and X. X represents the node feature of the images. And if we apply a reload activation function, we obtain this X bar that is our representation of the graph embedding. And as you can see, we are not using the normal adjacencies matrices, but we are using a normalized adjacencies matrices. As you can see, we have the inverse of the diagonal matrices multiplied by A and then multiplied again for the diagonal matrices up to inverse and so on. Okay, have a look at the embedding space. The embedding space, the embedding of the graph is just the output of a graph convolutional network. Okay. Let's see as low let's say as sorry. Okay, we have this embedding space that is just the output of the graph convolutional network. Okay, let's see how they work. Okay, suppose we have our graph with this small graph with some node features. They goes into our encoder, and we have this node embedding in a latent space with two dimension. What does it mean? Here, our embedding is an embedding for each node of the network. Okay. So how can we build the decoder? Okay, let me just recap. We have our graph. The graph goes into the decoder, and the encoder produced a node embedding for each node of the graph. Then what we want to rebuild our input graph. Okay. And here we are, how we can reconstruct the input. Well, the first paper that introduced graph autoencoders used the inner product between latent variable z. What does it mean within a sigmoid function? But what does it mean? That the adjacencies matrices, the reconstructed adjacencies matrices in position A and B is the sigmoid function of the product of the embeddings of A and B, and so on for each of the nodes. And here, just to show you what we have everything. We have our one convolutional neural network to do an embedding. We have our embedding that is just the output of our graph convolutional network. And then we have the inner product within a logistic sigmoid that reconstruct the adjacencies matrices of our graph. Okay. Go to the practice side. Well, in order to talk about the PyTorch geometric, already implement the graph autoencoder model, and it came from the same paper I'm presenting here. That is okay. Simply, how this model works. we call this model, we give as an input an encoder and a decoder, okay? And the decoder by default is the inner product. So we don't have to do so much. Let's see this in practice. I didn't ask, is everything clear so far, or it's okay?
Yeah, I think it was very clear.
Perfect. Thank you. Okay, let's start. You can download both the slides and this notebook from the official website, but let's see how it works. Here you can find the link to the paper and the code. The code that I'm using came from the official PyTorch geometric repository, and it's just copy and paste, and I'm here to show you the part. Okay, first of all, we are going to download the dataset. As you can see from we are going using site ser, that is a dataset that is downloaded. And then, as I already told you in the previous section, is interesting because if I rerun this line, we don't have to re-download the data because it has already stored in this folder that I specified here, this name here. Okay. Have a look at the data. We have an edge index of size 2.9000 so far. We have a test mask, training mask, and validation mask. Because here we are in a we have a unique graph, okay, and we are doing operation in a unique graph. So we have just one graph. We also have X, that is our feature matrix. And in particular, for each node, we have 3,703 features, okay? And also we have the labels. Okay, we don't need the labels because we are using this dataset in an unsupervised task. So what we do? First of all, we reset the train mask, the validation mask, and the test mask, okay? And if we have a look at the data set now, we have the same edge index. We have X and Y. Actually, we don't use Y. It's just here, but we don't use it. Then what we do? We call this function that came from PyTorch geometric tutorial utils. What does this function do? Well, this function just split the edges of the data, producing a new data set, actually the same data set, but we have negative edges, positive edges for test, for train, and for validation. Okay. It's obviously that test and train and validation, we know what they are used for. Why we have this negative and positive? Well, the negative are edges that are not in the graph, while the positive are edges that are present in the graph. Let me just say only this thing, just to have an idea. Okay. Now we have to define our the encoder. Okay. How the encoder is. In this case, we have this really simple encoder. We just define the name of the class we want. We inherit by the torch and then module. We initialiate the superclass. Okay. And then what we have? We have two convolutions. The first is a graph convolutional network with as the input channel, our input channel, the number of feature. Then we have an output channel with 2 multiplied by. So because we have two convolutional neural network, we goes from the input feature to the double of the output feature. And then with the second convolution, we go from the double of the output feature to the output, the real output feature, the embedding we want to, the size of the embedding we want to produce. Okay. Then we also have this cached equal true. This can use only on transductive learning. So in our case, because what it does, it caches the normalization of the diasynthesis matrices. So for instance, if we would have many graphs, it won't be useful to store this information. But in this case, in which we have only one graph, is it useful? Okay. And then we have the forward method that it's just call the convolution to x and the edge index, apply a ReLU, okay, and then return the second convolution. It's quite simple, okay. Now what we have, we just called our guy, graph autoencoder model, and we define our model simply calling guy and passing our encoder, okay? The only, the decoder, as we said previously, is by default the inner product. We specify, previously I specified the out channel, so the embedding in 2 dimension. Number of feature is taken from the dataset object, and the number of epochs. Then what I do, I just move the data and the model to the CPU, if to the GPU if it's available. In my case, is available, so both model data and edges are moved to the device, so to the GPU. And the last thing, I'm initializing the optimizer. Easy. Then I have these 2 functions, the train and the test. What does the train do? Well, first of all, it puts the model in a training mode. I put the optimizer in the 0 grad. I encode the model. So as you can see, well, let me show you. If we have a look to our models, so just model, you can see we have the encoder and the decoder. So what I'm doing below, I'm just saying model dot encode, and I pass the information to encode the data, okay? Then I compute this loss, that is a reconstructed loss, and this function is already gave me from the Gaia model, okay? In fact, if I do, it should work. I should have also this reconstruction loss, recon loss, okay? So this one is a function given from the implementation PyTorch. Then what I do, just backward on the loss and a new a step in the optimizer. Okay. Then the test. What does the test function does? Well, we put the model in the evaluation. We set torch no grad, okay, and we encode our positive edges, our training data, and we test the training data with positive and negative edges of test. In fact, in the below, when I'm calling the test, I'm passing the test positive edge index and the test negative edge index. Okay, it's quite easy, as you can see. I'm running 100 epochs, and we have done. Okay, so how we can use? We just want to, I don't know, we want to see the encoding in 2 dimension, and here we are. We have encoded our input in this information, and it's really done what we have to do. But I have a question for you. As you can see, the model returns AUC, that is the curve under the rock. So just to show you is this one. We have the true positive and the false positive and the rock curve, and the area above the ROC curve is defined as the AUC. And then we have the average precision. But if you have a look to these results, at least to me, is complex to understand and keep looking at each values and so on and so forth. For this reason, we can use Tensorboard. Tensorboard is really a useful tool, let me say. So how we can use it? First of all, we have to import Tensorboard. And then here I'm just cut and pasted what I did previously. It's just cut and pasted, really. And then if you don't have Tensorboard installed, you can just install it through pip. So pip install Tensorboard. You have to specify a folder in which you want to write your experiment results. Like, for instance, I call it Guy experiment, 2-dimension, 100 epochs, because we have set the out channel equal to 2. After that, I can run my model. So what's next? Next, I can move in the folder in which I have run the experiment and in which I stored these runs, Guy experiment, blah, blah. And I can open a terminal and just digit Tensorboard minus log dir equal runs. Okay. Now, if I'm connecting to this web app, as you can see here, I can see the average precision in train and the accuracy in train, okay, or test or whatever I want. And I can zoom in a portion. I can see bigger. I can do a lot of stuff. But why is it so important to have this kind of picture? Suppose that we realize that 2-dimensions are too few to embed our data, our nodes. So what I can do is just, instead of 2, write 20, rerun our model, maybe changing the name, and instead of 2-dimension, write 20-dimension, run it, run the training. And then what happened? If I update the page, you can see that a new model appear. Guy experiment 20-dimension, that is the blue one. And here you can compare the model, okay? How the model performs, changing parameters of the model. And I think it's really, really cool to see, because we can see that the model with 20-dimension has really a huge improvement with respect to 2-dimension. Well, it was kind of obvious, let me say, but I don't know, maybe looking at this image, I can think maybe I can try more epochs, for instance. So I can just, I don't know, 1000 epochs, change the name to the model, and run again. And here again, if I update the image, there is a new model, that is the red one. And okay. As you can see, the model tends to stabilize to, I don't know what is 0.88, okay? And however, the main idea of this tool is to visualize results, okay? And I think it's pretty cool if we want to visualize the output of our models. You can do a lot more with this tool, like you can build the computational graph. If you have images, you can visualize the images. It's really, really a cool instrument, but as everything, I want just to introduce you, and then it's the last thing I want to say is that there is this parameter that allow you to make the function more smooth or less smooth if we want to see, I don't know, details, or I don't know. Or we can see the trend of the function, increasing the smoothness of our results. Okay. It's done. We did the graph autoencoder. Okay. Let's move to variational graph autoencoder. What? Okay. Okay. Variational autoencoders. Okay. So far, what we see that what we have seen that if we have images, graphs, whatever you want, with autoencoders, you can embed it in a specific point. Okay. What happened with variational autoencoders? Well, instead of moving an image in a specific point, we move it in a multivariate Gaussian distribution. What does it mean? It means that we don't have the specific point like these 2, 5 coordinates, but we have a mu and a sigma squared. Okay. How it works? Again, we have the encoder, but instead of producing an embedding in a latent space, we have the parameter of a multivariate Gaussian distribution. Okay, let's go into details. What we want to do, suppose we have x, that x is our input, and z, that is the parameters of our multivariate Gaussian. Okay, and this one is our encoder. The decoder is the opposite, which is the probability of x given z. Okay, if we open it, so if we open with bias, we can see that the probability of x given z is equal to the probability of z given x times probability of x divided by the probability of z. Okay, where the probability of z is the multivariate Gaussian. QDX is the distribution of the input, and QDZ given x is something similar to our encoder. Okay, so what we want to build something. We want to that q PDZ given q, PDZ given x, and QDZ given x will be as much similar as possible. And what we can do here is called KL divergences that measure the distance between distribution. In particular, we want to minimize the KL divergency. Okay. Is it done? Nope, because we cannot compute q of x given z given x. And moreover, we want the reconstruction and our previous similarity. However, it has been proven from the authors of this work that this function here can be applied, and which is the difference? That the KL divergences is on PZ given x and Q of z. And moreover, we have this another term, okay? And interestingly, if we have a look on the specific term, we can see that the first term is a variational lower bound. Practically is the reconstruction error. How well the network is able to reconstruct our input, okay? And the second part is the regularizer, in which we keep the distribution of QDZ and PDZ given x both as much similar as possible, okay? And we can use this loss here. to train our model. So this one is the model. We have our encoder. Instead of having the random the embedding, we have this embedding in a multivariate Gaussian, and then we random sample from this multivariate to generate something new. Okay, which is the problem? Backpropagation doesn't work if we use random sampling. But here we have a trick called the reparameterization trick. How it works? Well, Z is not a random sampling, but Z is given by mu plus sigma pairwise multiplication of epsilon, in which epsilon is a random sample, normalized normal sample with mean 0 and sigma equal to 1. Okay? And this trick is called the reparameterization trick, and it allows you to do backpropagation. Can you see the right image? So we can do backpropagation on each sample, and without taking in consideration epsilon, our random sample. In this way, we can skip the problem of backpropagation. Okay, move to graphs, because what I did so far was an introduction to variational autoencoders in the general framework. We have to move to graphs. And what's changed? Again, we have our encoder, our latent space, and our decoder. How the encoder works, he has two convolutional neural networks. So instead of one, we have two convolutional neural networks. The first one is the same we used before, so the graph convolution with a ReLU activation function and with the normalization of the adiasynthesis matrices. And then we have a second graph neural network that generates mu and log of sigma square. So we have this graph convolutional network mu that takes in input x and a, and it has this learning parameter w1, okay? And then we have log of sigma square. Why we are using log? Because in this way, we don't have the problem of negative numbers, because the graph neural network can produce a negative number, but with the logarithm, we put it in a positive way, okay? And again, is a graph convolutional network with the same learning parameter W1. To put together, we have this graph convolutional network here that is the adiasynthesis matrices normalized, multiplied by the ReLU activation function of the normalized adiasynthesis matrices, multiplied by the input vector, input feature vector, and W0, and then we end W1. If you can see, the inner is the first graph convolutional network, and the second, the wall equation, is the second convolutional neural network. And here we are. Then what we have, our reparameterization trick. So mu plus sigma, pairwise multiplication of epsilon, that is normally distributed. And then we have our decoder that is identical to the previous one. So the inner product between latent variable of Z, okay? And again, to a sigmoid function that tells us if there is the edge or there is not the edge among that nodes. Okay, move to the practice. What's changed? Well, nothing, let me say. Instead of having our graph convolutional network encoder, here we have a variational graph convolutional network encoder. Let's see the structure. We inherited from Torch and Yen module, instantiate the superclass. We have the convolution one that takes in input the input channel, goes into output channel, doubled output channel. So, okay. So again, these previous tricks in which we start from the number of feature, we reduce, and then we go to the output feature, okay? Then we have the convolution mu and the convolution log std. And again, we have to multiply the output feature. So the second neural network, again, here and here. Okay. We have then the forward method in which, first of all, we use the first convolution, the real activation function, and then what we return is the output of the, we are returning two outputs. One is the convolution mu, and the second is the convolution of log standard deviation. Okay? Again, as previous, we can specify the number of out channel, the number of feature, the number of epochs, and what's new? Nothing. Instead of use a GAE model from Torch, PyTorch geometric, NN, we import VGAE, variational graph autoencoder, and we instantiate the model passing our encoder. Because again, the decoder is the inner product by default. We move the data to the device. So in my case, again, the GPU. Okay. And finally, we initialize the optimizer. The train is identical to the previous one, with the difference that the loss is not only the number of the reconstruction loss, but it has been combined with the KL loss, KL divergences. Okay. Oops. So we just combine these two kind of loss, apply the backward and the optimizer step, and return the loss. The test is identical, and the train, it's identical again. Let's just run these lines. As you can see, I introduced this, I also used Tensorboard here so that we can compare the results. In our case, we are comparing 2-dimension 100 features. And again, if I move to Tensorboard and I go down, I can see here, variational graph autoencoder experiment 2-dimension 100 epochs. And I want to compare with the GAE experiment 2-dimension 100 epochs. And done. It's done. Okay. Maybe I have to decrease the smoothness of the function. Okay. Since here seems that the our GAE model works better than our variational graph autoencoder, but we can also try to, I don't know, for instance, increase the number of epochs. And it's too much. Let me just do, I don't know, 500. I didn't change the name. Sorry. Okay. If we go again here, and suppose we want to compare this model here with, I don't know, something else. Okay. As you can see, we are achieving more or less the same, in some sense, performance, but it was just an example to show you how it's easy to compare, and you can, for instance, zoom in or have a more detail in some part about fluctuation. It was just to show you the idea of graph autoencoders and the power of Tensorboard. Okay, I think we have done. Okay, are there any questions?
Antonio, I have actually 2 questions.
Yeah.
The first one is, correct me if I'm wrong, but so basically with graph autoencoders, you basically can use it only in a transductive setting. Whereas with the variational autoencoders, are you able also to use them in an inductive setting? Because since you're learning not the representation in the latent space, but you're learning the distribution from which to sample, is it true that maybe you can use it, the variational autoencoders, for an inductive setting of graphs?
Well, definitely you can use variational autoencoder in an inductive learning framework. But I'm asking why you think you cannot use the simple autoencoder in a inductive manner?
You said so. That's why.
Oh, sorry, it was my no. I was saying that. Sorry, it's my fault. I was saying that you can use only these. Sorry, cached parameter.
Okay.
But
so
you can you can. This cached parameter is just to let me show you here that it's quite easier. Oh, sorry.
But probably I understood it wrongly.
No, maybe I say something graph. Okay, it was just that cache. Oh, sorry. Okay, this parameter here, cached. What does it do? It's just instead of compute every time the normalization, it computes once because the input graph is just one.
Okay.
But you can use autoencoders in an inductive manner.
Okay. The second question, if you can go back to the slides.
Sure. Okay.
Should be around 77, something like that. No, here is fine. Here is fine. The number 75.
Okay.
Okay, so here you're basically learning this multivariate Gaussian, right?
Yes.
So basically, again, it's unclear to me. So basically, here mu will be a vector, right?
Yeah.
Values. How do you go from having a matrix, because basically the GCM produces a matrix of values, right? Which is one vector for each node.
Yeah, but mu here is a vector. Let me say. The idea is that. Sorry. The idea is that for each, from the encoder, each the output of the graph convolutional networks goes into mu, and it produces one mu for each embedding space and one sigma for each embedding
dimension, basically.
Yes, dimension, sorry. So yes, the idea is that you learn one mu for each dimension and one sigma for each dimension. So for instance, if the output
yes. What I'm saying is that GCN outputs a matrix, right?
Yeah, one
like n times d. n is the number of nodes, and d is the dimension of the of each node, basically. Mu would have basically dimension 1d, right? And also the sigma.
Yes, I see your point. And
I was wondering if, I mean, it's just
actually,
you know, if you have any idea on how you go from having this matrix representation to actually getting the mu.
You're right. You're right, because you're totally right, because here the output, okay, it's an output channel, but you are right, one for each node. So there is some kind of
I mean, maybe there is some pooling operations.
Exactly. I'm not aware of which kind of pooling there is, but you are totally right. Yes.
Okay. Maybe we can check out.
I can check out. Thank you. Sorry.
Thank you for the presentation. It was very nice.
Thanks. Sorry, yeah, I totally missed it out. Yeah, but you are totally right. Yes. Thank you. And perfect. Are there other questions?